welcome to our team's engineering design project presentation. On this website, we'll walk you through our design journey from identifying a problem to building and reflecting on our final solution. Our team focused on accessibility and gardening. We wanted to help elderly individuals or those with physical limitations continue enjoying this rewarding activity without the strain it usually involves. On this page, you'll see our problem statement and target stakeholders. The core issue we addressed was that traditional gardening involves repetitive bending, lifting, and watering, which can be a major barrier for people with mobility challenges. Our primary stakeholders include older adults, people recovering from injuries, and those with chronic physical conditions. We also considered caretakers and family members who assist with household activities. Now we could relieve some of that burden. Spaces and constraints. Moving to our specifications, we had to keep our solution under $100, compact, enough for an indoor or balcony use, and able to use functions semi-autonomously. It also needed to be easy to operate, even for someone who isn't very tech savvy. These constraints helped narrow down our ideas and encouraged us to focus on simplicity, durability, and modularity. Ideation and concept selection. Here you'll find our sketches and idea board. Here you'll find our sketches and idea board. We brainstormed a rotating plant stand, a mobile gardening cart, and a smart watering system. Each one was sketched and evaluated based on cost, complexity, and usefulness. We used a decision matrix to compare ideas across 4 categories: effectiveness, user accessibility, cost, and reliability. The highest scoring concept was the AutoGrower 1.0, a moisture sensing water unit with LED alerts and a compact footprint.
Time frame for our product. Our product will span across 3 months, where we have our first prototype available to stockholders and anyone who is willing to invest in our prototype. So they'll have the first available model, and then test prototypes, which will be available through our website, so users can give us feedback and other data that would help create a more efficient model. And then we have our public release, which will happen in the last and final month of the time frame, and it will provide us with more overall general customer satisfaction and more feedback in general. Our deliverables here, as you see, our first prototype is month 1, test prototype month 2, and month 3 is a public release. Between these months, the little time between these months allow us to take additional feedback we get from our investors and provide more of a fleshed out model. And we also have our focus groups here, which range from the elderly to more young people too, which give us a wide range of how we can make our app more user friendly and how we could overall improve on the final product. The resources we use at AutoGrow are always of high quality. The pot that houses the plant holds our electronics. The water tank makes sure that the water is available with our sensors, detect that the plant needs water, power source, and with a wall adapter. So a basic power cable that plugs into a wall to ensure it has proper power. Our grow light, which provides mock sunlight to it to allow it to grow, and a water pump that moves the water from the tank to the plot, and then a microcontroller to house all of our data and make sure that the sunlight sensors are working and we're getting enough feedback from the plant. With these sensors, they also detect that the plant needs water or it needs less water, and is the plant receiving enough nutrition or light. Our budget for this was $100,000. We put 30% of it into manufacturing, 30% of it into prototypes, 10% into basic testing, 15% into focus group, and 15% into advertising. The manufacturing is estimated at $30,000 because we intend to get favors from our warehouse and factory managers that will help reduce the cost. The testing and focus groups take $25,000 because the testing is done in a controlled environment, such as if you're in Texas, you're your plant will be acclimated to more of a hotter climate than compared to like a coastal climate. So this takes a large amount of our budget. And the focus group tests are also used so we get more of a fleshed out app to allow everyone to be able to use it in an easy way. Advertising takes the final 15,000%. The use of billboards and online ads, and we will be using social media as our main platform to really promote our product. The risk and implications. The market itself is not as big as we hoped it would be. Um, the elderly and physically impaired individuals lose access to gardening solutions, and a delay in delivering innovation that's already been developed and tested. Approval matters because low maintenance and wide appeal makes AutoGrow 1.0 attractive to a larger customer base. Minimal effort required after setup increases customer satisfaction and retention. Positive brand image through inclusive problem-solving technology. Cost of inaction outweighs investment, both financially and socially. How do we measure our success? Who the product goes to, why the product is being bought, amount of product being sold, satisfaction of customers. Is advertising adequate? You see the graph on our left shows how that's what we want our profit margins to look like, just a continuous um, in the up direction. This is our website. Thank you for watching.
Our main objective was to create a bridge only using popsicle sticks, tape, and a ruler that could support a 3 to 6 ounce water load. That's roughly 0.4 pounds, which may not sound like much, but with limited materials, stability and structure became a key. For our bridge design, we went with a truss structure. This means we build triangular patterns into the side walls of the bridge. Trusses are common in real engineering because they distribute weight more evenly and reduce bending under pressure. We briefly considered other layouts like a flat beam bridge and an arch structure, but those either lacked strength or were harder to build consistently with popsicle sticks. So we landed on the truss structure because it gave us a good balance of stability and material efficiency. The materials we used were wooden popsicle sticks, a regular tape, and a ruler just for measurements. So the approximate cost came out to being $541. We kept the design lightweight and efficient without overbuilding or wasting any unnecessary sticks. On this page, you'll see photos from the construction process. We began by assembling flat truss panels, two identical sidewalls with triangular bracing. Then we attached them to a flat base layer and used cross beams for support. Each joint was reinforced with tape, especially around the central span where the water load would be placed. Consistency in spacing and alignment was really important to prevent sagging.
Alright, on this page we have our final demo for our bridge. So as you can see in this video, we found a half full sort of Windex bottle to use to test our bridge. And we found that the structure held up perfectly. There was no major collapse. Here, I'll pause it right here. On our bridge, there was no major collapse or major flexing, which confirmed that our truss design and joint reinforcements worked as intended. So the platform was stable, the bridge didn't rock or shift under load, even when we nudged the table slightly. We even did more tests where we even dropped the bottle from a distance onto the bridge, and it withheld like at least 4 of the tests. Then overall, we were very happy with how our bridge build went. Our measurements were consistent, our truss design gave us more strength than expected. Even though we used lightweight materials, such as the popsicle sticks, which are very hollow and not that heavy, we had a lot of strength within our build. One surprise to us was that some tape slipped under tension, especially in like the warmer room temperatures we had. So to fix this, we had to double tape. We had to reinforce our tape that we had to kind of help the stress points on our bridge, because a lot of our points on our bridge were under a lot of tension the way we had designed. So another challenge was keeping the base straight while assembling. The popsicle sticks kept moving and sliding under the tension, so we had to make sure everything was flat and would stay together. In the end, the challenge helped us understand how basic materials work together. We understood smart geometry, and that our design helped us um, have a lot of strength in our build. And we learned load dispersion and joint strength techniques. And that was our assignment. Thank you.